Hey, hi everyone. Welcome to this new problem that we're discussing. This is problem number 322 called coin change. So it states that we are uh, you're given an integer array coins which are representing the possible denominations of coins and an amount, right? So the question is like how many return the fewest number of coins that you need to make up that amount. So let's say that the amount that we are given is something like 11, right? And we know that 11 could be made up with different sets of coins, right? For example, we can have like six 1 rupee coin and then a 1 5 rupee coin to make it. But that would be 7 coins, right? But the fewest number of coins or the least number of change would be if you are taking two 5 rupee coins and then adding 1 rupee coin to it, right? So that's three coins. So that's the least. So that's example one. Also, it's possible that you are given a coin and then the amount that you are given cannot actually satisfy it. For example, here, let's say you only have a denomination of 2, right? And then you are asked to create, pay amount of 3, right? That's not possible. You cannot, you don't have 1 rupee coin to make that amount. So that's not possible. So in those cases, we will return -1. The third example is, let's say we are given 1 rupee coin. You have a denomination, but then the amount is basically 0. So to have 0 amount, you don't have to have any coin. So you return 0 for that, right? So that's a base case. Then let's say if you have like 1 rupee coin and the amount that you are needing to pay is 1, then the output is 1. That's example 4. Right? So let's look at how we can do this. So we have basically a bunch of coins. We have a bunch of coins that we'll be passing. And these coins are basically going to be the denominations like 1, 2, 5, 10, etc. And then we have an amount, right? We have an amount of, let's say, 31 rupees. Then that's going to be 3 times 10 rupees plus 1 time 1 rupees, right? So it's actually 4 coins in total. So yeah, so that's how we would have to do this breakdown. But let's think of what would be a recursive way to solve this. Okay, so let's say we have 31, right? Now so what we can try to do is you can see how, let's say, when I'm trying to do make this use this coin, I can try to break it down into smaller problems, right? 1, 2, 5, 10. Let's say these are my options with respect to coin. So let's say that I pick basically I'm trying to ask the question. Let's say if it is like something like 2, right? If the amount is 2, then what is the number of coin that I would have to have this how many coins would I need to, what would be the minimum number of coins that I would need to represent let's say amount of 2 rupees. So it's basically going to be what? So we know that for 2 it's going to be 2 into 1, right? But if you look at 1, it's going to be 1 into 1, and if you look at 3, it's actually 3 into 1, right? And then it goes till 5, because at 5 what happens is yeah, you can do still 1 into 5, but there is a better alternative in form of 5 into 1, right? So, and this is the better number of coin, right? So the idea is you sort of build this kind of sub problems, and you would actually solve the problem by break it down into smaller sub problems and then solve it in a bottom up approach. So here the thing is, let's say if you are going for a purely recursive solution, you would end up solving the same sub problem multiple times. Like let's say what is the least number of coins needed to, let's say, have the amount of 5, right? That sub problem will come not just in f of 5, but let's say if you're doing f of 10, and then I remove the I use the first fifth coin, and then I will still get f of 5, and that f of 5 I would have to again solve, right? So so this is a bit like, let's say, the Fibonacci sequence problem, right? So Fibonacci sequence, you know that fib of n is basically fib of n minus 1 plus fib of n minus 2 for all n greater than 2, right? So the interesting part is, let's say you're trying to solve fib of 4, then that means you have to solve fib of 3 plus fib of 2, right? When you do fib of 5, you have to solve fib of 4 plus fib of 3. So you can see that you are repeating the same problem. I mean, you're solving the same problem again and again, right? So instead, if we can actually store this value of fib of 3, or what is the problem that's being repeated somewhere, then that can actually mean that you can reduce a bit of time in terms of the time taken to do that compute. This repetition of the computation that you already done can be solved. So that's essentially what dynamic programming is. It is this idea that, let's say you have a problem, and this problem you're able to break down into sub problems, right? Sub problem 1, sub problem 2, etc. Let's say sub problem n, and when you have, let's say, solve sub problem of 1, you put it somewhere, you cache it, right? So you cache it, and then when you're actually trying to solve this sub problem again, and then if you're trying to get the result, what you do will be like you would basically get that result from the cache instead of recomputing it again. And this could be done in two ways. One is top-down DP. The other is bottom-up DP. So in the top-down approach, what we would do would be we would have something, we'll do a memorization. Basically, we will sort of pass a cache inside a recursive function. In the bottom up, what you do would be like you will have a DP array, and then you would, even in memorization you will have a DP array, but you would start filling it from let's say the base case. Like, let's say if you're trying to solve it for Fibonacci, we would start the array with the base case of what are the values for, let's say, fib of 0 and fib of 1, and then you sort of extend the results there, and what you would eventually return in your function will be, let's say if this is the DP array, you would basically return the element that is basically there for that particular index, which would be the result, right? So it's basically a kind of a trick, and let's see how we would be able to do this in for this particular problem. So I'm moving to LeetCode now. Okay, let me change to Python. Okay. So what I'm going to do first is I'm going to initialize a DP array, and this array I'm going to fill it with some default values. But before filling the default value, the size of this array has to be basically size of the amount plus 1, and I'm going to fill it with because we are going to also include 0 for the handling the base case. So I'm going to put basically the amount plus 1 as the default value, because we know that if there are 31 coins, so 31 rupees, right, you will never have 32 coins. So this could be something that I can use later to give basically that -1 when you have denomination that cannot be represented. I will use this logic to kind of handle it. So then the next part is to handle the base case, right? So let's say if the amount is 0, that means basically the result is 0, right? There's nothing, no handling that you have to do. There's basically no coin, right? Then what we have to do is we need to iterate from case starting from 1, because 0 we have already handled, but when the amount is, let's say, from 1 to amount plus 1, because its Python range is not inclusive, so we iterate through this. So that's the top level loop, and then for each amount that we are looking at, right, there are possibilities of all the coins that could exist. So that will be for C in coins, right? Now these are the different possibilities of the different coins that could be used. Let's say for one, you would have basically let's say here the amount is 1, and here the possibilities are, let's say, 1, 2, 3, 4. Then yeah, it doesn't make sense to check for coins which are actually greater than the denomination value of coin, right? So we would have an if condition here, which would say if if the amount value is greater than or equal to coin, right? Only then we should kind of get inside this loop, right? Otherwise, let's say if the amount is the coin value is, let's say, the amount is something like, I don't know, 0, then there's no point in it cannot be represented. So maybe this is a bad example. Let's say if the denominations were something like 2, 3, 4, then there's no point in getting inside this loop, right? If this was the case. Okay, no, I think I messed up this if condition. It's actually not if I minus I less than or equal to C. It's more like, let's say, let's think of the case, right? Let's say when the coin is, and the amount is, let's say, when I is equal to let's say 10, then, or let's say it's 2, when I is equal to 2, right? So amount is 2. Then what we should be checking is I minus C. We should be checking if, let's say, C is 1, then this value should be non-negative, right? What does that mean is, let's say if I is equal to 2, then there is no point in going to coin equal to 3. So, right, you cannot represent coin 2 by um, amount 2 by coin 3. So the condition here is going to be, if I minus c is greater than or equal to 0, right? Only then start looking at these points, otherwise you can just ignore, right? So now this is where we would want to like initialize our DP array now. So if I minus c is greater than or equal to 0, then that is actually a coin that we should consider, right? But we should not blindly consider it. We should check whether, so for example, when let's say we have the coin 5, there's going to be different ways of doing it, right? One would be 1 into 5, right? That's going to be one other way, and then there's going to be 5 into 1, right? So in both the cases, you would be actually satisfying this criteria of I minus c greater than equal to 0. But we should pick basically the one which is having the most minimum value there, right? That's what we should be assigning between all the possible combinations. So we should have a min, right? And we should take into account the existing DPFI. And in this case, if you are getting to this for the first time, it's going to be amount plus 1, right? And then increment this with 1, and then do dp of I minus c, right? Because the assumption is that we would have already solved for the subproblem, that is I minus c. It would have been already solved. So we are incrementing, basically considering this coin that we are adding plus whatever is the result already from, let's say, doing dp of I minus c, right? So that's pretty much it actually. So then basically what we want to do is return dp of amount, but we need to do handling here, return dp of amount if dp of amount not equal to amount plus 1, right? Because that means we haven't found anything optimal. In such cases we have to return minus 1. So that's the code. So if you look at it, first what we do is we assign basically this DP array, right? And then we handle the base case, which is for, if there is 0 amount, then we are going to basically initialize it with 0. Then we iterate basically from 1 to amount plus 1, right? And we have another nested loop for iterating to all the possible coins. And we obviously want to look at conditions. This is kind of a convenience method, right? We don't want to look at coins which are going to be non-negative, right? I mean, when we subtract the coin value from the amount, it should not be lesser than 0, because those are the only valid coins, right? So let's say if the number of coins here was like 10, then you cannot use a 10 rupee coin to pay for a single amount, right? So this ensures that sanity checking. And then we come to the minimization step. So it is about checking, basically iteratively replacing, right? I mentioned this case. Let's say if the amount is 5, if the problem that you're trying to solve is DP of 5, then DP of 5, initially when the coin is 1, it would be actually filled with basically 5 as the value, because right, you'll have 5 coins that could be used to represent it. But then when you reach coin, when the coin iteration becomes at 5, you would realize that you would quickly get it by doing 5 into 1, right? So that is basically why we do this. We have two arguments to this minimize function, the existing dp(i), and then we are essentially doing 1 plus dp of I minus c. So essentially what this will do is, like in case of 5, it's going to be dp I minus c in this case will be equal to 0, right? So it will end up calling dp of 0. So dp of 0 is what? It's already 0, so it's going to be set as 1, right? So that's how this works. So, and then yeah, basically it's just checking whether, if the amount is not equal to amount plus 1, and then returning minus 1, etc. So let's try this code. Yeah, this seems to work. Okay, so that worked. That's all. Thank you.